Let's look at the concept of capacitance. Here we have, say, a conducting object all by itself, and let's come and put a charge on it. So in a static situation, we know the charge will reside on the outer surface, and there will be no tangential electric field on the outer surface, otherwise you would have charge motion. And the electric field therefore emanates out normal from the surface, say something like this. Now let's let V represent the potential of this object. So the potential difference between this object and infinity, or in other words the amount of work it takes to bring 1 coulomb of charge from infinity to this object, is minus the integral of E dot dl from infinity to the object. Since there are no electric fields inside the object, the potential is the same everywhere on the object. It's an equipotential object. Now, for reference, let's let the voltage at infinity be 0. So the potential of our object is minus the integral from infinity to the object of E dot dl. Okay, and let's assume the amount of charge we currently have on that object is plus Q. Now, let's go and add another plus Q to the object. So we're doubling the charge, and clearly the total electric field is going to be doubled. So we've doubled the charge. If we've doubled the electric field everywhere, we've doubled the voltage. So we see that the ratio of the charge on the object to the potential of the object is going to be a constant. And that constant is called the capacitance. And so it will have units of coulombs per volt, which is designated as a farad in honor of Michael Faraday. Let's determine the capacitance of an isolated sphere of radius A. So the way we do this is we would go and we'll put some charge, Q, on the sphere. And because of the spherical symmetry, we know the electric field intensity will radiate out in the radial direction from this sphere. So here's a representation of the electric field intensity, and we know that the electric field intensity will be equal to the total charge we have on the sphere divided by 4 pi epsilon sub 0 r squared. The only component of the electric field is in the a sub r direction, and this is valid for r greater than a, because for r less than a there is no electric field intensity. So for this charge Q on our sphere, let's determine the potential of the sphere. Okay, so the potential difference between the sphere and infinity, and if we choose infinity again, a reference potential there to be 0, the potential on our sphere is minus the integral from infinity to a of E dot dl. So that's the amount of work it takes to bring 1 coulomb of charge from infinity to our sphere. So let's put in the form of our electric field intensity. And now we have to dot it with our differential length. And in a static situation, the path we take does not matter. So let's just take a path along a radial direction. So d sub L is going to be d sub r in the a sub r direction. So AR dot AR is 1. Let's factor out Q over 4 pi epsilon sub 0. Those are all constants in this case. Okay, so if we perform this integral, we'll get a minus 1 over R, which we'll evaluate between infinity and A. So the potential of our sphere is Q over 4 pi epsilon sub 0 times A. So the capacitance is just the ratio of the charge to the potential of our sphere. So the capacitance of a sphere is 4 pi epsilon sub 0 times its radius. Now let's look at the concept of a capacitor. You have a capacitor when you have two conductors as shown. Now let's take and apply a potential across these two capacitors. So we're applying some voltage V. So we know we'll get some positive charges on this object on the left, corresponding negative charges on the object to the right. The electric fields will emanate normally from the object on the left and terminate normally in the object on the right. So maybe something like this. So you'll have some corresponding electric field, and you can integrate the electric field from the object on the right to the object on the left and get the potential drop across them. In other words, the value of the battery or voltage source that you are applying. So now let's change the potential. And we change it in such a manner, we increase it so that we double the charge on each object. And so you're going to clearly double the electric field intensity because you're doubling the number of electric field lines that are emanating from the left-hand object and terminating on the right-hand object. So again, the potential is the integral of minus E dot dl from the object on the right to the object on the left. So doubling the charge doubles the potential. So the capacitance of our capacitor, Q over V, is again going to be a constant. Let's look at the procedure for determining the capacitance of some geometry. And we will look at this simple case of two parallel plates with a dielectric in between. So the spacing of the plates is going to be D. The dielectric will have some dielectric constant epsilon sub r, so the absolute permittivity is epsilon sub r times epsilon sub 0. The dielectric will fill the complete region between the plates, but for illustrative purposes I'm going to leave little gaps between the dielectric and the plates. And so the procedure we're going to go through will be the same if you have, say, different geometries like a coaxial cable or two parallel lines. So what we will do is we're going to put some voltage across the capacitor and thereby get some charge on the two plates. And then from that charge we're going to determine the corresponding the electric field and then relate that electric field to the voltage, and then we'll just take the ratio of the charge to the voltage. I've attached a voltage source such as a battery across our capacitor, resulting in a positive free charge on the plate on the left and a negative free charge on the plate on the right. Now we're going to assume that the plates are large enough area compared to the spacing between the plates that we can ignore the small contribution of fringing fields at the edges. So in other words, we're going to assume that we can determine the electric field pattern as being identical to that which we would have if we had infinite parallel plates. with a charge of Q on the left-hand plate and an area for that plate of S, the surface charge density on that plate will just be Q over S. Now, assume the plates are perpendicular to the x direction and the positive x direction is to the right. We know that the electric flux density field is just equal to the charge density on the positive plate, and its direction is in the x direction, or Q over S in the x direction for the electric flux density field. Now, the electric field is just the electric flux density field divided by the permittivity of our dielectric. So the electric field intensity will be rho sub S over epsilon sub R, epsilon sub 0 in the x direction, or Q over epsilon sub R, epsilon sub 0 S in the x direction. With the left-hand plate positioned, say, at x equals 0, the right-hand plate is going to be at x equal d. So then the potential drop across the plate, or V, is going to equal minus the integral from d to 0 of E dot dl, or minus the integral from d to 0 of our electric field, which is Q over epsilon sub R, epsilon sub 0 S in the x direction, dotted with dx in the x direction. So that's equal to minus Q over epsilon sub R, epsilon sub 0 S. Ax dot Ax is 1. So we're left with the integral from d to 0 of dx. So that will be minus Q over epsilon sub R, epsilon sub 0 S times x evaluated between d and 0, or the potential is Q times d over epsilon sub R, epsilon sub 0 S. And the capacitance is the charge over the voltage. So in this case, the capacitance for a parallel plate capacitor is epsilon sub R, epsilon sub 0 times S, the area of our plates, over D, the spacing between the plates.